Now we'll take a look at the reactions of acid halides, and we covered this already before, so it's just going to be a review here, but I just want to reiterate that and organize everything again, put everything together for acid halides. And in this case, the chlorine's a leaving group, and we're going to add a Grignard reagent here. In this case, it's a methyl Grignard, so that's why a methyl group replaces that chlorine leaving group. But this forms a ketone, and ketones can undergo nucleophilic addition with a Grignard, and that's why you go one further step. And so the first reaction with the Grignard is a substitution reaction. So, and the second one is an addition reaction. So if it adds two equivalents, you add excess. That's kind of the way it works. If you want to add only one equivalent, actually we need to change up the reagent and use something less reactive, and that's your Gilman reagent here, a lithium dialkyl cuprate. So in this case, the copper alkyl bond is less polar and therefore less nucleophilic, and that's what you use if you want to stop at the ketone. Next, for acid halides, we're looking at hydride reduction. Again, we already reviewed this, and you're going to use lithium aluminum hydride here, and it will reduce it 2 steps. And the first step is just simply a nucleophilic acyl substitution, replacing the chlorine with a hydrogen, making an aldehyde, and then you do nucleophilic addition to make the alcohol. And it turns out, just like with the Grignard, if you want to stop at one equivalent, you can't do it with lithium aluminum hydride. You've got to use a different reagent, and you're going to use this big bulky hydride reagent, lithium tritibutoxy aluminum hydride, which looks like this guy. So only one hydrogen is the key here, and that's why, due to the bulkiness and also carrying it at low temperatures to restrict some things, that's why it's only going to react once, and you can stop at the aldehyde. And then we'll take a look at converting the acid chloride to all the other carboxylic acid derivatives. And again, since the acid chloride is the most reactive, you can convert it into any of them, to the acid anhydride, the ester, the carboxylic acid, or the carboxylate, as well as the amide. All of them are possible. And if we take a look at how this works here, I've kind of summarized it here as well on your sheet, but it's really all summarized in this chart. So if I want to make the acid anhydride, I want to replace that chlorine with a carboxylate, and so I can simply just add the carboxylate. Or I can use the neutral nucleophile and use a carboxylic acid. One thing to remember, though, is with acid chlorides, we do need pyridine in there to act as a base. If I wanted to make the ester instead, well, to make the ester instead, I'd use an alkoxide, diagrammed here, or the neutral species would be the alcohol. And again, with starting with acid chloride, I also need that pyridine there. So I could also make an amide here. So to make the amide, I either add the amide anion, or I'll need 2 equivalents, so we can write excess of the amine. Now, if you notice here, I used a primary amine, whereas on the chart here, I used a secondary, and technically you can use an unsubstituted. You can use NH2- and NH3, just depending on which amide you want. Do you want an unsubstituted amide, a primary amide, a secondary amide? All of them are possible. And then finally, the carboxylic acid, as well as the carboxylate. The carboxylate's always hydroxide for all of them. But the carboxylic acid, here I've got written H3O+, but again, that's technically H+ and water. That's the acid catalyzed mechanism, and we don't generally do acid catalysis with acid chlorides. We just would simply add water, but again, put some pyridine in there to act as a base.